Over the last few episodes, we created a custom schematic symbol, created the schematic, made a custom footprint, associated footprints with schematic parts, and generated a netlist. We're finally moving into the layout stage with pcbnew. Here, we'll import our netlist, arrange our parts, draw a board outline, and make trace connections. On this episode, we'll look at arranging our parts, which is one of the most important steps you can do before connecting things with traces. From the KiCad Project Manager, select Tools, Run pcbnew. The first thing I like to do is fill out the document information section, so click File, Page Settings. We'll keep the revision the same as the schematic, so write V01. For the title, write 555 badge and leave company blank. On the fourth comment line, write author, your name. Write license, CC by 4.0 in the third line, and creativecommons.org/licenses/by/4.0/ in the second. Click OK, and you should see the title block populate with your information. The next thing I like to do is make sure I'm working with the right units and grid. Like I mentioned in a previous episode, most board houses use the imperial system, so it's usually easier to keep the inches button selected. We'll be changing the grid often during layout, but I like to leave it at 50 mils during the part placement stage. Then, we need to import the netlist we generated on the last episode. Click Tools, Netlist. Make sure that the 555badge.net file is correctly listed and leave everything else at default. Note that if you make changes in the schematic and need to re-import your netlist, you'll likely want to select Change Footprint to import any new footprint changes you made and click Delete Extra Footprints to remove any unused parts. Click Read Current Netlist. Once that's done, click Close. You should see all your parts appear in the center of the page. Before we go any further, we should set up some design rules to prevent us from putting parts or traces too close together. This will ensure that the board house can actually fabricate our board. To start, head to oshpark.com. There are lots of board manufacturing houses out there, but Oshpark does a great job of making it easy to order low-quantity PCBs for things like projects and prototypes. Click on Services and click See All Services. We'll be making a 2-layer board, and this is where you can find information about their fabrication capabilities. The 6mm trace clearance specification tells you that you can't have traces closer than 6/1000ths of an inch away from each other. Also, all your traces need to be at least 6 mils wide. Drill holes need to be 10 mils or larger, and the annular ring should be at least 5 mils. You can also see pricing information here and see that we need to order things in batches of 3. We'll need to know these rules as we enter them into KiCad, which will help us lay out our board within these specs. Normally, this is all you would need to set up your design rules, but Oshpark has gone the extra mile and given us exactly what we need to enter into KiCad. Click on Support at the top and click See All Docs. Click on KiCad and go to Manually Set the Design Rules. Here, you can see what KiCad rules Oshpark recommends. Don't worry, I'll walk you through them. It can be helpful to put KiCad and the Oshpark rules side by side. Click Dimensions, Pads Mask Clearance. This determines how much space there should be between a pad and the start of the solder mask. Oshpark wants this to be 0.002 inches, so we'll change it to that. Click OK and go to Design Rules, Design Rules. Go to the Global Design Rules tab. Make sure Do Not Allow Blind Buried Vias is selected, and make sure Do Not Allow Micro Vias is also selected. Blind, buried, and micro vias are useful in multi-layer boards or boards with very tight component spacing. However, Oshpark isn't capable of fabricating them, so we don't need to worry about them. Alright, since I mentioned vias, we should talk about what they are. Let's go back to our PCB cross-section. A via is almost exactly like a through hole in the board. In fact, it's made the same way. The copper and substrate layers are drilled, copper is added using an electroplating process. However, vias are usually much smaller than through holes, as they aren't meant to hold pins or wires. Their purpose is simply to connect traces or copper between layers. If you have a trace on the top layer and you want to connect it to the bottom layer, you would use a via. We'll use one or two in our layout. This is where things can get a little wonky. The Osh Park KiCad docs show different dimensions than what we looked at on the services page. The services page is probably the correct one, but to be safe, let's go with the one that has larger widths and spacing, which is on this page. Change the min track width to 0.006 inches and change the min via diameter to 0.027, which is the total width of the via including the drill hole and both sides of the annular ring. Then change the minimum via drill diameter to 0.013. Change the U via diameter to 0.027 and its drill diameter to 0.013 to match the regular via dimensions. U via stands for micro via, and we need to enter these values so that KiCad doesn't yell at us. However, Osh Park will ignore these since they won't fabricate micro vias anyway. Go to the Net Classes Editor tab. We've entered the absolute minimums for spacing and sizes as per our board house specifications. In this tab, we can change how big and how far apart our traces will actually be. You can make other trace sizes, but I'll cover that on the next episode. If you can, it's a good idea to make your traces, vias, and spacing a little bigger than the board house's minimum specifications. When you're working with boards that have a lot of space, like this one, a clearance and width of 10 mils is usually a good starting point. So change clearance to 0.01 and track width to 0.01. Let's make our vias slightly larger than the Osh Park minimums, so change via diameter to 0.03 and via drill to 0.015. Even though we won't use them, change the micro via diameter and micro via drill to 0.03 and 0.015 as well. Click OK. At the top left, you should see your track width and via dimensions shown. The next step is to move the parts around so you can get an idea of how big your board should be. Hover your mouse over a part and press M. If asked, pick a footprint to move and move it out of the way of the squished part huddle. Just keep moving parts until there are no parts on top of each other. Do you see the white lines connecting the various footprint pads together? These are called air wires and are very helpful in figuring out how parts should be connected with traces. The entire group of air wires is known as a rat's nest, and that's because the nest of a rat is a messy clutter of straw, which kinda looks something like this. You can click the Hide Rat's Nest button to toggle the air wires on and off. Now comes the tricky part, untangling the rat's nest the best you can by moving parts around. Each time an air wire crosses over another air wire, you'll likely have to move that trace to a different layer. You can't just cross them on the same layer because you'd create an electrical short between two nodes that aren't supposed to connect. The idea is that you want to minimize the number of times you have to move to another layer. On very complicated boards, 2 layers won't be enough, so you'll need to use a 4-layer board or a 6-layer board or even more. But we're going to try to do everything with 2 layers. Move the parts around by pressing the M key and rotate them with the R key when they're on your cursor. Experiment with different positionings until you think you've gotten it down to the least number of air wire crossings as possible. Remember, we can't have components touching, otherwise they might short together. Most of the parts have a gray bounding box called a courtyard. Make sure the bounding box of one component doesn't cross into the bounding box of another and you should be good. When you're pretty happy with the general placement of the parts, begin squishing them together, making sure not to overlap any courtyards. For surface mount projects, you will have to remember to leave some space between parts if you think you'll need to get a trace through them. You can always move parts around later, but it becomes harder as you'll likely need to redo traces when you do. Note that I'm leaving the LEDs out as they'll be separate from the rest of the parts. If you had an idea of the shape of your board, you could put your parts in that shape as you were moving them around. If you want an even tighter layout, you can right-click on a part, select Footprint, and click Flip. This moves the part to the other side of the board, where you can technically position it underneath other parts. This does not work well with plated through-hole parts, as the pins will usually stick through and poke the part on the other side, making it hard to solder. Even for surface mount boards, having parts on both sides is usually more difficult for assembly shops to make them, so you'll get charged more. It's generally good practice to have parts on one side of the board if you can. Now, let's make our board outline. Search for ID badge size, as we want our board to look like a standard badge. ID wholesaler looks good, so click on that. The CR80 is the most common size. Let's use that. Let's modify the dimensions slightly to make it easier to work with in our program. Don't worry, the tolerance on the board edge of most PCBs isn't the best, so you won't really notice the difference. We'll go with 2.12 by 3.37 inches. Back in KiCad, click the Add Graphic Line button and select the Edge Cuts layer. This layer is where our board outline should go, and it'll tell Osh Park where it should cut to make our board shape. We can't move the origin of our layout sheet. It's always stuck at the top left corner just outside the border. So I'm going to pick an arbitrary coordinate and pretend it's the origin. Let's say x equals 5, y equals 5. Hover your mouse over 5, 5, press space to place a temporary marker so that our relative xy coordinates will show 0, 0 at that point. Click to start a line and click again 4 more times to make something like a rectangle. Press escape to end the line. Hover your mouse over the first vertical line and press E. Make sure the line starts at 5, 5. The end x should be 5 since this is a vertical line. The end y should be 3.37 inches above the start y. So 5 minus 3.37 is 1.63. Remember, down is positive in the y direction in pcbnew. Most board houses, including Osh Park, like the board outline thickness to be 1 mil to avoid any confusion about where the cut should occur. So change the thickness to 0.001. Click OK. Hover over the next line and press E. Make the starting point 5, 1.63 to connect it to the top left corner. The end y should be 1.63 as this is a horizontal line. 5 plus 2.12 is 7.12 for the end x. Change the thickness to 0.001 and click OK. Edit the next vertical line and change its starting point to 7.12, 1.63, and its end point to 7.12, 5. Change its thickness to 1 mil and click OK. Edit the final line and change its starting point to 7.12, 5, and its end point to 5, 5. Change the thickness to 1 mil and click OK. Press Escape to end the line drawing mode. Click and drag to create a box around all the components except for the LEDs. We'll do this to move them all as a group or block. Leave the block operation selections as default and click OK. Move your components to completely inside the badge at the bottom. They don't quite look centered, so what we can do is change the grid size to something smaller, like 20 mils. Highlight the parts again, making sure you don't include any of the board outline lines in the group, and move them over until they look more centered. Check to make sure no parts or pads are outside the board outline. Go back to a 50 mil grid. On many boards, you may want to add mounting holes so you can attach it to something with screws. For our badge, we'll want to add an oval cutout at the top so we can clip a lanyard to it. Head back to docs.oshpark.com and click on Cutouts and Slots. If you read carefully through this section, you'll see that we should make the cutout on the board outline layer, and it needs to be bigger than 0.1 by 0.1 inches. Somewhere near the top of your board, draw 2 parallel horizontal lines on the edge cuts layer. Click on the Arc tool and draw 2 arcs near the lines. Based on some measuring and a little bit of trial and error, I will tell you that the slot should be about 0.4 inches long and about 0.15 inches wide. So edit the first line. It should start at 5.86, 1.73, and it should end at 6.26, 1.73. Make the thickness 0.001 and click OK. The other line should start at 5.86, 1.88, and end at 6.26, 1.88. Make this one 0.001 inches thick as well and click OK. The first arc should be centered about 5.86, 1.805 with a starting point of 5.86, 1.73. Make the arc angle negative 1800 and the thickness 0.001. Click OK. Make the second arc centered around 6.26, 1.805 and have the starting point be 6.26, 1.73. Change the arc angle to 1800 and thickness to 0.001. Click OK. You should have a nice oval shape for a cutout. Move the LEDs to the center of the open area. I like to rotate them so that the negative flat edge is facing down. If you'd like to make them perfectly centered like I did on my board, you can move D1 to 5.81, 2.95, and D2 to 6.31, 2.95. And that's it. Click File, Save to save your work. Moving components around to minimize cross-tracings is a very important step, and it'll make drawing those traces much easier, which we'll do on the next episode. Click that subscribe button if you want to see more fun videos like this, and see you soon.